received the telephone call.
Just after Christmas in 1987, I was called down to Folkestone to a baker shop in the town centre. I knew a body had been very badly burnt because the smell was recognisable. This is where the body of Barrister Dane was found. The remarkable thing about it is that he was so badly burnt, but the rest of this kitchen was hardly touched by fire. For instance, there was a dustpan and brush made of polythene only inches away from the body, and there was a small air vent made of plastic. That had a small amount of charring on it. The ceiling was made of polystyrene tiles, and these weren't touched at all. My first thought that he'd been murdered and moved and burnt. Looking around the area, we couldn't see any reason for why he'd been murdered. We then thought that he might have committed suicide by pouring some petrol on him, but there was no matches or any cans in the kitchen.
Bodies soaked in petrol have been known to burn without damaging the rest of the room. But when forensic scientists examine these unusual fire deaths, they invariably find a much more straightforward cause of death. Careful scientific investigation has shown that these cases turn out to be nothing more than a tragic accident.
Igniting now. In every case of this type that I've examined, I have found a perfectly good ignition source present in the premises, be it an electric fire or a gas hob, often coupled with evidence that the victim has either ignited his or her own clothing, or objects have been ignited in the immediate vicinity of where the victim has collapsed. The two cases you've told me about are very similar to the types of fire that I have examined in the past. It's clear from the photographs, however, that there are viable ignition sources present even on first inspection. In the one case, there is an electric fire next to the hole in the floor, and in the second, there is a gas hob present right next to the victim.
This indeed was the cause of the fire in Folkestone.
Having ruled out murder and suicide and spontaneous human combustion, the only thing left for the death of Barrister Dane was that he's had a heart attack, caught himself on fire by the lighted gas stove, fell to the floor and then burnt like a candle from above and downwards.
The idea that a body can burn like a candle isn't such a far-fetched one at all. In a way, a body is like a candle inside out. In a candle, we have a wick on the inside with the wax on the outside, and as the wick burns, the candle is made molten and the liquid is drawn onto the wick and burns. With a body, which consists of a large amount of fat, the fat melts and is drawn onto the clothing, which acts as a wick and then continues to burn. Fat is drawn onto clothing much the same way as the fat in this dish is being soaked up into the piece of cotton I have shown here. Now I'm going to do a short experiment to illustrate the wick effect with a piece of animal fat. I'm now wrapping it into a piece of cotton, and I will set fire to it by means of a match. And the first thing that happens, of course, is that the cotton begins to burn, and it will burn of its own accord. But the moment the flame approaches the animal fat inside, the fat will begin to melt and become soaked onto the fabric, and that will begin to burn as well as the cotton itself. In fact, as the cotton burns, it is rendered down to a rigid char, and that acts as a very effective wick for the burning of the animal fat below. There's a lot of water associated with fat and indeed with the human body, but there's sufficient heat liberated in the burning of the fat itself to drive water off in the form of vapor ahead of the burning zone.
But some things remain unexplained. How, for example, can the bones be burnt to ash? And why are just the limbs left behind?
I have dealt with many bodies that have been burnt in fires of all sorts, house fires, aircraft fires, high-octane fuel. I've never come across a body in which the torso was burnt away and the extremities were left, the extremities in this case being the feet. The normal pattern for a body burning is, if it's in a very serious fire, then the extremities will get burnt away, the torso will be blackened, but never have I come across a torso that's been destroyed by fire.
The pattern of burning can be determined by the position of the ignition source, but it's also worth bearing in mind that, of course, The majority of the fuel on a body, the fat, is located around the centre of the torso, and this of course is the area, once the fat has rendered out, that is going to be exposed to most of the flames. Limbs contain much less fuel and therefore are likely to be the last things to be destroyed in these fires. In some cases the fire goes out without having extended as far as the ends of the limbs, so therefore we find the limbs lying around the edges of a burnt hull.
Well, I cannot see how a human body can catch fire and burn away like that. If human bodies were so readily flammable, then we wouldn't need to expend all the vast quantities of energy in crematoria to get rid of corpses.
In a crematorium, you need high temperatures, around about 1300 degrees centigrade or even higher, to reduce the body to ash in a relatively short period of time. But it's a misconception to think that you need those temperatures within a living room to reduce a body in the same way. You can produce local high temperatures by means of the wick effect and a combination of smouldering and flaming to generate the temperatures necessary to reduce even bones to ash. At relatively low temperatures, at about 500 degrees centigrade, given enough time, the bone will in fact come down to something approaching a powder. The experiment we're going to carry out here simply involves putting an animal bone in a muffle furnace at just over 500 degrees centigrade, and the intention is to leave it for about 8 hours and observe what happens to it. Well, the bone has certainly changed markedly in appearance. It's white on the surface and looks quite friable. And over a period of 12 hours or so, it is quite likely that the bone would smoulder slowly enough to reduce it to a powder. And certainly we can see the starting process involved here, because parts of the bone are clearly very much weakened and will just fall away as a powdery dust. I believe that the combination of the wick effect and the involvement of the bone, which could act as a wick itself, giving a smouldering process, will give rise to sustained severe burning of the bone itself, accounting for the type of damage that has been attributed to the so-called spontaneous human combustion.
But this doesn't solve the mystery of why only certain objects in the room are damaged by the fire.
Well, at first sight, this picture does look rather mysterious. We've got television damaged in the right-hand side, and although there's a lot of smoke staining, nothing else seems to have been damaged by the heat. But if you consider it, this situation is not as mysterious as it first appears, and in order to understand it, you need to understand about the mechanisms involved in fire growth. You see, fire isn't a haphazard process. It involves a certain number of well-established stages, each of them involving well-known physical and chemical processes. In an outdoor fire, fire grows by a process of flame contact. You ignite the first item and the flames from that go on to ignite another item and so on. But fires inside a building are quite different. A different mechanism takes over. And if you understand that mechanism, you can understand this picture. When you ignite the first item inside a room, the heat and smoke from that first item rise into the upper part of the room and form a layer under the ceiling. And as the fire progresses, that layer gets hotter, but it also gets deeper and thicker. And eventually the layer descends until it starts to touch other materials standing on the floor of the room, such as the television set. And you can see from this photograph that the television set must have been immersed in that layer, and the layer must have been hot enough to cause melting of the plastic material in the TV case. And we have a computer model which will allow us to find out what type of fire produced this type of damage. And if I input the melting point temperature of the television case and the details of the room, the height of the ceiling, the floor area, the fact that the doors were closed, and the general volume of the space involved, we can find out what happened in the fire. Ah, right, this is very interesting, because the computer program is telling us that at 260 seconds, the oxygen level in the room was reduced to 16%. Now, this is a very important level because oxygen in air is at 21% normally. But in a fire in an enclosed room, the oxygen level will go down because you're abstracting oxygen from the atmosphere. And when the oxygen level reaches 16%, this has an important effect on the fire. It suppresses burning, and the fire is likely to diminish in size and go down to a low burning type of fire, smouldering fire, if you will.
To test his computer prediction, Stan Ames attempted to recreate the same type of smouldering fire that took place in Southampton, using an armchair to represent the burning body, set up in a room with low levels of oxygen. The progress of the fire was followed with an infrared camera.
Right, that seems to be burning. We can get out of the way now. Right, I think we need now to close the door so that we can seal off the room and recreate the ventilation conditions we designed. Now we can watch the fire through this window and follow it with a specially designed infrared camera. The oxygen concentration in the room to start with is about 21%, and as the product burns, this concentration is slowly reduced. And when it gets to about 16%, this low level of oxygen starts to interfere with the burning processes, and the fire will start to extinguish itself and go back to a low, smouldering sort of fire.
The most important feature of this experiment is to demonstrate that the smouldering process could sustain itself long enough to reduce a body to ash, or in this case, the armchair to its springs. 6 hours later.
The chair has burned almost to completion. There are black marks up the wall where the fire has occurred. There are deposits of oily material on the ceiling. Broadly speaking, the kind of damage we'd have predicted from our computer model. So really, this is broadly what we expected to find. It can all be explained in terms of ordinary physics and chemistry.
So it seems that nearly every aspect of these mysterious fire deaths can now be explained. Some source of ignition will have caused the body to burn. The heat dries out the body so that condensation forms on the windows. Once the body is dry, the fat melts and orange fatty deposits build up on surfaces like the light bulb. Because this fat doesn't burn cleanly, black soot sticks onto the doors and walls. If the body is undiscovered for a long time, the wick effect will give way to a slow, smouldering fire, and the temperature in the room will rise, often heating up metal objects like the doorknob. As the hot gas layer produced by the smouldering fire descends, it will melt plastic articles in the room, like television sets or the plastic face of the clock. Because newspapers and seat covers burn at a much higher temperature, they will appear untouched by the hot gas. Smouldering will continue until the body fat or the oxygen in the room runs out. It would seem that the mystery is finally over.
For some people, the existence of spontaneous human combustion is a matter of faith, and no evidence in the world is going to convince them otherwise. As a scientist, I'm quite satisfied that spontaneous human combustion does not exist.
As mysterious as it first appeared, Alfred Ashton's death is now easily explained by Roger Penny.
Mr. Ashton was seen alive at approximately 6 o'clock. Neighbours the other side smelt burning at about 10 o'clock, so I would assume that somewhere between those two times the fire began. All we could assume is that the gentleman fell on the fire, or close to the fire, and gradually the radiated heat ignited the body and slowly smouldered, in time burning through the floor and indeed the cable.
And during Saturday the wind was becoming even stronger, very stormy indeed.
This explains why the television and the electric fire were off the next morning. The burning body had cut off power to the original source of ignition. So even in the most bizarre of these cases, it seems there's no need to resort to the supernatural. Science can provide a perfectly rational explanation for all of these deaths.